Let's start with today's lesson, which is on numerics and geometric patterns. As always, let us get a clear understanding of the concept we will be working with today. First of all, what are numeric patterns? A numeric pattern is a sequence of numbers that follow a certain rule. So pay close attention to that. It's a sequence of numbers that follow a certain rule. We have different types of numeric patterns. The first one being the arithmetic sequence, which is a pattern where the same number is added or subtracted each time. In this pattern, we have, in this example that we are given, we have 2, 5, 8, 11, and 14. For them to be able to get to the next term, they had to add 3 to the previous term. So this is all that happened. For them to get to 5 from 2, they added 3. For them to get from 5 to 8, they added 3. For them to get to 11 from 8, they added 3. And for them to get to 14 from 11, they added 3. So this type of pattern is called an arithmetic sequence, where the same number is added or subtracted each time. In this case, it was our 3. Now we have the second one. We have the geometric sequence. In a geometric sequence, a pattern where each term is multiplied or divided by the same number is classified as what we said in the beginning, a geometric sequence. So this is a pattern where each term is multiplied or divided each time. So for example, we have 3, 6, 12, and 24. For us to be able to get to the next term, we multiplied 2. And for us to be able to get to the next term, we multiplied 2. And from 12 to 24, we also multiplied 2. So this type of sequence or numeric pattern is called a geometric sequence. And then we have square numbers. So this pattern can be formed by squaring whole numbers. So for us to be able to get to the next step, we squared whole numbers. So here we squared 1, hence we found 1. Here they squared 2 and they found 4. Here they squared 3, their result was 9. Here they squared 4, their result was 16. And here they squared 5 and their result was 25. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared is how they were able to conclude this pattern. So this is called a square number, which is a pattern formed by squaring whole numbers. The fourth one is a triangular pattern. So this pattern is a pattern where numbers can form an equilateral triangle. An equilateral triangle is a triangle where all the sides are equal. For example, we have 1, 3, 6, 10, and 15. So here they found this by adding or finding the sum of the first n, we don't know what is n, natural numbers. We will do more examples of it for a clear understanding. Let us now go to describing the rules. We can use words to describe each pattern. If, for example, you are asked what happened in a pattern for you to be able to get the next value, you can say you start at 2 and add 3 each time. So that is how you can describe your pattern in words form. For example, the pattern that we did above, where we added 3 to get to the next value, we added 3, we added 3, we added 3. So we started at 1 and we added 3 each time to get to the next value. Now let us use another way in which we can describe it is to use algebraic expressions to describe the nth term. E.g., for example, if you had 2, 5, 4, 8, 11 as your sequence, then the rule would be that Tn, which is your term number n, will be equal to 3n minus 1. So this just says this sequence follows this rule, which is how we describe a numerical pattern at the beginning. So now let us learn how to find the nth term, because this is confusing. But now we are going to learn how to determine this so it becomes less confusing and eventually it doesn't become confusing at all. So to find the nth term, you first have to identify the first term and the constant difference or ratio. So we have a general formula for arithmetic, a general formula for geometric sequences. These are the only two formulas we have. So these general formulas are what we are going to use to find our TNs. Remember, we had different types of number patterns or numerical patterns. And for each different pattern or sequence, we have a different general formula. So for arithmetic, I showed you what an arithmetic sequence is. And for geometric, I showed you also what a geometric sequence is. So now we are just going to go ahead and learn how to find the Tn. So for arithmetic, you have Tn, which is equals to A plus into n minus 1d. For geometric, you have Tn, which is equals to A multiply R n to the power of n minus 1. Let us learn more about geometric patterns. So a geometric pattern involves shapes and are based on rules of size, position, orientation, and repetition. So here are the types of geometric patterns. The first one, we have a growing pattern, which is when the shapes increase in number, size, or complexity. That is what we call a growing pattern. So for example, because it's a shape, we can have one square and then have two squares and then have three squares. Number two, the second type of a geometric pattern is called a shrinking pattern. So this shape decreases in number or size. Number three, we have what we call a repeating pattern. These are the shapes that repeat in a specific order. So for an example, we could have a triangle, a square, triangle again, and then a square again. This will all make sense when we do more examples. The fourth and last type of geometric patterns, we have the symmetrical pattern. So this is the pattern that mirror across a line, which is called the line of symmetry. The line of symmetry is a line that cuts two different parts into equal sections. Let us move to how we can describe a geometric pattern. Just like an arithmetic pattern, we can use words to describe the pattern, like saying we added one square each time in a row. Secondly, we can use diagrams or drawings to show the growth or repetition. For example, this is what we can use to show the growth or repetition of the geometric sequence. So now, how do we analyze patterns? We can analyze patterns by firstly identifying how the shape changes, the size, the number, the color, or the position. That is how we can analyze a numerical pattern if we are given one. Secondly, we can count elements to find a number pattern hidden in the shape. Okay. Thirdly, we can link numerical patterns with geometrical growth. For an example, the number of tiles in a pattern. These tiles is the geometrical part, and the pattern is the numerical pattern part. So that is how they are linked. We can find the number of tiles in a pattern. Now let us do algebraic representation of our numerical patterns. We first start off by converting the geometrical pattern into a formula. So for example, if the number of dots in the pattern grows as 3, 6, 9, 12, then the general term will be T is equals to 3n. This is done by simply, the n means the position. So if you were to put excuse me. If you were to try to find which number holds position 1, you will have your 3. If you were to try to find which number holds position 2, that would be 6. If you were to find out which number holds position 4, that would be that would be 12. Position 1, position 2, position 4. If we were to try to find position 3, we'd find it as 9. So here are general strategies for pattern work. This is how you can find the TN or the sequence or the rule that the pattern follows. So firstly, you look at the consistency. You look for consistency in change. Secondly, you use tables to organize terms and find a rule. Thirdly, you can draw diagrams if needed. And fourthly, you can explain the pattern both in words and an algebraic form. So that is how those are general strategies you can use for pattern work. The fifth one is to practice both describing and predicting patterns. So here are important vocabularies or keywords you need to know when dealing with number patterns. The first one is a term. So a term is a single number in a pattern. Term is a single number in a pattern. The constant difference is the fixed number added in an arithmetic pattern. For an example, if we had 3, 4, 5, 6. So we added 1 to get to the next term, added 1 to get to the next term. This 1 is referred to as our constant difference. Another important keyword we need to know is ratio. What are ratios? These are fixed numbers that are multiplied in a geometric pattern. The fourth one we need to know are sequences. So what are sequences? These are ordered list of numbers or shapes. The fifth one is a rule. What is a rule? It's a description or formula that generates the pattern or that the pattern follows. Now we will go on to worked examples to get a clear understanding of what we were doing. For our example number 1. We are now going to be dealing with an arithmetic pattern. So it's a numeric pattern, also known as a numeric pattern. So the pattern we are given is 4, 7, 10, 13, and 16. So remember our key points we learned about how we can strategize on a numerical pattern. So the first one was we look for consistency in change. We can use a table to organize the terms and find a rule. We can draw diagrams if needed, and we can explain pattern both in words and algebraic form. We can also practice both describing and predicting the pattern. So let us first try to figure out the rule or the sequence or what our pattern is following. So this is basically the rule. So for the rule, we look for consistency. For them to be able to get to 3, and for them to be able to get to 7, and for them to be able to get to 10, and for them to be able to get to 13, and for them to be able to get to 16, they added 3 each time. So now you see the consistency in the sequence. For them to get to the next term, they had to add 3. So now we can find the nth term. Remember we said for Tn, for arithmetic, Tn is equals to A plus into n minus 1d. Our A is the first term of the sequence. Our D is the constant difference. So here is how we are going to find the nth term. We are going to do this from our original equation. We added, our first term was 4, which is our A. We put 4 here. Our nth term is what we are looking for, so this does not change. Minus 1 is originally given to us. And our D is the constant difference. What was the constant difference? 3, because we added 3 to get to the next term, added 3 to get to the next term, and added another 3 to get to the next term. So ultimately, we have Tn, which is equals to 4 plus into n minus 1 multiplied by 3, which is this. So now, our Tn is equals to 4 plus distributive law, 3 multiplied by n, and 3 multiplied by minus 1. We have 4 plus 3n minus 3. The like terms, we group the like terms. Our Tn will be 3n, 4 minus 3 is 1. So that is how we got this Tn. They asked us to find the 10th term of the sequence. And here's how we found the 10th term of the sequence. N just means the position, which is the number in which the term holds in our sequence. So they asked us to find the 10th term. We had 3 multiplied by 10. That is where we substitute our n, plus 1. Eventually, we have 3 multiplied by 10 being 30 plus this 1. So the 10th term will be 31. Let us move on to the second example. Or before we move on to the next example, let us give one more example for this arithmetic pattern so we get a clear understanding. example number 2. Say we are given our pattern as 3, 8, 13, 18, 23, and so on. Just shows that our pattern continues. So now we first look for consistency, which is the rule. And the rule is, for us to be able to get to the next term, we had to add 5. So that is our constant different, plus 5. So our rule in words can be written as add 5 each time. Let us try to find the nth term. Our Tn is equals to a plus into n minus 1d. Remember, our a is the first term of the sequence, which is 3. Our d is the constant different, which is 5, 5, 5. So we are going to look for this nth term. Now we have 3 as our a, n we don't know, and d as 5. Applying the distributive method, our 5 multiplies the n, and it also multiplies the minus 1. So now we have 3 plus 5n minus, 5. Our Tn ends up being 5n minus 2. And let's say they asked us to find the 20th term. So the 20th term will be our n. We will multiply the 20 minus 2, which is equals to 80 minus 2, 78. So that is our 20th term. Sorry, excuse me. 5 multiplied by 20 is 100. 100. So our 20th term is 98. So the way in which we can prove if our Tn is correct is if when we substitute term number 1, we get the first term plus 1. It's going to be 3 plus 1 is equals to 4. So here is how we can confirm our Tn is correct. So we know that this Tn is basically the nth term formula for this pattern. So now if we substituted our term number 1 as 1 plus 1, we got 4, which is this. Term number 2 is equals to 3 into 2 plus 1 is 7, which is our term number 2. Term number 3 is equals to 3 into 3 plus 1, which is equals to 10. See? Term number 4 is equals to 3 into 3 into 4 plus 1 is equals to 30. So that is how we can confirm if our equation is correct. Let's move on to example number 2. So this is for geometric number patterns. So we will see in the sequence that for us to be able to get to the next term, we looked for consistency, and we saw that we multiplied the previous term by 2 to get to the next term. We multiply 2 by 2 to get 4, 4 by 2 to get 8, 8 by 2 to get 16, 16 by 2 to get 32. So that is our rule. Multiply by 2. Our nth term formula, remember, compared to arithmetic, we said the formula for the nth term is Tn, which is equals to A. Let us go check the formula again. A multiplied by R to the power of n minus 1. This is a second example. A multiplied by R So the way in which we are going to work this out is we already know that A stands for our first term of the sequence. As we said, A is our first term of the sequence. And in this case, the first term of the sequence is 2. So our Tn will be 2 multiplied by, what is the ratio? The ratio is 2, n minus 1. So now they asked us to find the sixth term. Remember, you can confirm this by putting 2 multiplied by 2 to the power of 1 minus 1. It will be 2. So you can confirm if your general term formula is correct by looking for your term number 1, which is equals to 2. Remember, it's supposed to give you 2 times 2 to the power of 1 minus 1 will be 2. Term number 2 is supposed to be 4. 2 times 2 to the power of 2 minus 1 is equals to 4. And then the term number 3 is 2 times 2 to the power of 3 minus 1 is equals to 8. So that is how you confirmed if your general formula is correct. You can only test with 3 terms so that it does not take too much of your time. So now they asked us to find the sixth term. We are going to say term number 6 is equals to 2 times 6 times 2 to the power of 6 minus 1. This is equals to 2 times 2 to the power of 6 minus 1, which is 2 times 2 to the power of 5, which gives us 2 times 32, which is 64. So that is how we were able to find our sixth term. Now let us go to example number 3 and look for square numbers. We first look for consistency. It's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So they squared each natural number. A natural number is the number from 1 to infinite. So they squared each natural number, starting with 1, 2, 3, 4, 5. So that is the rule explained, which is our consistency. Now for the nth term, we have Tn is equals to n squared. So you can test this by saying term number 1 is equals to 1 squared, this one. Term number 2 is equals to 2 squared, which is 4. Term number 3 is equals to 3 squared, which is 9. So now they asked us to find term number 7. Term number 7 is equals to 7 squared, becoming 49. So that is an example on square numbers. Now we will be doing an example on triangular numbers. So our pattern says we have 1, 3, 2, 10, and 15. We look for consistency, and if you can check, they added 1, and then they added 2, and then they added 3, they added 4, they added 5. So we can say that they added 1, then 2, then 3, then 5. Supposed to be 0 here. So finding the nth term, we have Tn, which is equals to n plus 1 all over 2. Let us confirm if it is correct. Term number 1 is equals to n into 1 plus 1 all over 2 gives us 1. Term number 2 is the same as 2 into 1 plus 1 over 2, which is equals to 3. This cancels this, and then you get 3. So that is how we found our nth term, and they asked us to find term number 5. We now have T5 as 5 into 5 plus 1 all over 2, which gives us 15. So our term number 5 will be 15, as we already have it there. So now let us go to example number 5, which is growing. Geometric patterns. So a row of squares increases by 1 each time. Term number 1 was 1 square. Term number 2 were 2 squares. Term number 3, we had 3 squares now. Give my squares if they don't look like squares. So we look for consistency. When we find the consistency, which is our rule, we find out that they added 1 square per term. And now we can say that Tn is equals to n because we added, if you put 1, we get 1. Tn is equals to T. Term number 1 is equals to 1. Term number 2 is equals to 2. Term number 3 is equals to 3. So now they asked us to find the 8th term, which means T8 is equals to T8 will be equals to 8. Moving on to example number 6, which are the shrinking patterns. So we have our pattern being 100, 90, 80, 70. So for us to be able to get to the next term, we notice that they subtracted minus 10 each time. So we can now say that the Tn is equals to 100 minus n minus 1 multiplied by 10, which is our difference. And now we have 110 minus 10n, which it will be our Tn. So we can test this like we always did and say T1 is equals to 110 minus 10 into 1, we will have 100, which is our first term. So now we know if we test with our second term and our third term, we will find 90 and 80. So now they asked us to find the term number 6. Term number 6 is going to be equal to 110 minus 10 into 6, which is 110 minus 60, which is equals to 50. So now we'll move on to example number 7. For example number 7, we have repeating geometric patterns. At first, you see they had a triangle, and then a circle, and then a triangle, and then a circle, and then a triangle, and then a circle. So they repeated every 2 shapes. So now they asked us, what is the 11th shape? So we can divide 11 by 2, which will be equals to 5, and our remainder will be 1, which means the 11th shape will be a triangle. But if you do not want to use this, you can simply test the method by drawing your patterns. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is your 11. Remember, we had this in how we can strategize our patterns. Now we are going to complex arithmetic patterns. So they added 6 here. They added 6 here. They added 6 here. Our Tn, remember for arithmetic patterns, is n, a plus n minus 1d. Our a in this case is 5. Our n we don't know, and our d is 6. So ultimately we will have 6n minus 1 as our Tn. And we can test the pattern, and they asked us to find the term number 12, which is just going to be 6 multiplied by 12 minus 1, which will be 71. So that is how we have term number 12. Moving on to our 9th example, we have visual patterns with dots. Term number 1 is a circle. Term number 2, we have 2 circles. Term number 3 is 3 circles. So each term has n dots. So which means that term number 1 has 1 dot, term number 2 has 2 dots, term number 3 has 3 dots. So which means term number 20, as they asked us to find us, will have 20 dots. Okay. Let us now go to example number 10, which are mixed pattern numbers and shapes. We have 1 and a circle, 2 and a triangle, 3 and a circle, 4 and a triangle. So our odd numbers have circles with them. Our even numbers have triangles with them. So for our consistency, we found out that the rule, there are alternate shapes and numbers increase by 1. So since 7, they asked us to find the 7th term, and since 7 is our odd, we can say it has a circle. If they asked us to find the 8th term, it will be like this, because we notice that our even numbers have triangles with them. So that is how number patterns work. I hope this was not too complex for you. If it was, practice these examples more and more again to get a clear understanding. And that will be it for our lesson for today.